Okay, and our next speaker is Nick Kunkel from Chronicle Labs, and he will be talking about their new protocol, Chronicle Protocol, Oracle Scalability at the Limit. Nick Kunkel, everyone.
Awesome. So hi, my name is Niklas Kunkel, and I'm the founder of Chronicle Protocol. Chronicle is essentially a infrastructure company, and we want kind of the crypto ecosystem to stop treating data like a black box and start asking questions about how do we verify the integrity of this kind of data? Where did this data come from? So many of you are probably not familiar with us, but we actually started out as part of the MakerDAO team. So we actually launched the first Oracle on Ethereum back in June of 2017. And we've been effectively securing the entire Maker protocol since then. So there's currently about $9 billion in TVL and MakerDAO that we're securing. And so from that frame of reference, that makes us the second largest Oracle provider in the entire crypto ecosystem right now. So I kind of want to start by just identifying the problem that we're trying to solve. So let's kind of take a sobering look at the Oracle landscape. So right now, when you think of an Oracle, this is probably kind of what you're thinking about, right? You're thinking about, here's some asset pair, here's some price, and great, now you can go read that price. But you don't really have any guarantees here, right? You don't know where did this data come from. You essentially don't have like any data availability nor data integrity guarantees. Furthermore, oracles are quite expensive. They're expensive to purchase as a service. They're also expensive to run. The gas cost for running oracles is quite significant. And coupled with the fact that gas prices are highly volatile and can, multiply from what is currently about 20 gwei, and we saw up to like 3,000 gwei, right, in the previous cycle, right? They can multiply to cost into the hundreds, sometimes even millions of dollars a year just in gas costs for a single oracle on Ethereum layer 1. And so this is just completely unviable for anything but like the largest and most wealthy and high revenue generating protocols, right? So what is everyone else supposed to do? So what we've done with Chronicle is we're trying to address three distinct challenges. We want data to be verifiable. We want it to be interoperable across any blockchain, and we want it to be scalable. So we want to get the cost per update down so low that we can update much more frequently and therefore have like a much more accurate oracle that relative to its reference. So before I can get a little bit more into the details, I kind of have to give a little bit of context of how Chronicle works. So Chronicle is based on a validator consensus model. And the types of validators that we use are essentially applications in the crypto ecosystem that you're probably used to using every day. And so essentially our trust guarantees come down to, well, if you use MetaMask, you're implicitly trusting in Fura, right? If you're, you have a mobile phone on your wallet, it's very likely you're using Argent, right? Maybe you have some open positions on DYDX, right? Maybe you manage your vaults, in Maker and Aave through DeFi Saver. Essentially, we want to get away from, okay, with Chronicle, you're trusting Chronicle, and kind of go towards this model of if the majority consensus of this community of validators up here tries to launch an Oracle attack, we have much bigger problems in our industry than just this Oracle attack. So if you look at our front end, this is essentially what it looks like. So you have a bunch of feeds, right? They're pretty much updating usually like multiple times a second on all of the different data types that we support. Oops, there we go. And essentially what is happening here is they're operating on this kind of like consensus layer. So this other kind of property that we really value is resiliency. And so what we essentially want is that there's no single point of failure or infrastructure that can be taken down, right, and just to take the whole protocol down. So when I talk about this like off-chain kind of consensus layer, what I mean is that we have one layer using libp2p. We have another layer using secure scuttlebutt. We have a third layer using Tor. And of these three, right, we can even add more in parallel in the future. But of these three, only one actually has to work for the entire Oracle protocol to function, right? So essentially, these consensus layers are just acting as like coordination mechanisms for attestation kind of aggregation between all of the validators. So now that we have this context, we can kind of go into this verifiable property that we want to go after, right? So with Chronicle, what we want to get to is you have a credibly neutral Oracle with verifiable data integrity guarantees. So how do we get there? Well, would encourage you to check out our front end again. This is kind of what you would see when you go visit, right? Here's, for example, the ETHUSD Oracle contract, right? You have this number, but what is behind the number? Where did this come from? How did we get here? How did we get to 1,813.50? And so essentially, you can click on any historical price and load up, okay, what were the exact validator responses for this specific price, right? So here we can see, right, that we have the responses that were submitted by all of the different validators. And you can see that Etherscan reported this 1,813.50 number, which, you know, surprise, is the same one that we had before, right? And so this validator was selected because it was the median out of the entire kind of quorum amount of validator set. But we can even go one step further, because rather than just identifying the individual validator responses, we can go and look, well, let's take a look at how did that individual validator, right, construct its price, right? And so you can see that, oh, well, it went to Uniswap v3 and it got this. It went to Kraken and it got this. It went to Gemini and it got that. These are all essentially contained within the stack traces of the signed like message attestations. And kind of in the future, the way that you would probably improve upon this is, one, you either want the individual sources to start signing their data. And there are some that are willing to do this. But more than likely, a more generalized use case for this is something like TLS. Right, so each individual query to each data source, right, has a corresponding TLS proof, right, that verifies that that data was not manipulated in any way. Cool. The other thing you can do is verify that the data that we're showing you in this dashboard is not BS. So you can see the raw signature, and then verify it locally in your browser and do essentially what the smart contract itself is doing. So you have this message right here, and you can click verify. And if it's a legitimate message, right, you get this green thing, right, saying that, yep, this validator, right, who was supposed to sign the message, signed the message. On the right side, all we did was we changed the timestamp by 1 second. So this age parameter, right? We tried to verify the message, and it doesn't work. So it's important that, you know, when we say, oh, like these crypto systems are transparent, transparent to who, right? Transparent to some Solidity wizard who's like hacking around on Etherscan and digging around in internal transactions, or transparent to everyone. And so verifiability, to me, is just this evolution of transparency where it's more accessible to someone like you or me. OK, and then the last property that I want to talk about is scalability. So scalability is essentially make or break for any Oracle protocol. You can either withstand the gas price volatility that we have in these boom-bust cycles in our industry, or you can't. And so even very, very minor reductions in gas can really, really add up once you start adding these multipliers of 100x gas price, right? 300x gas price. So what we've come up with is essentially an optimistic Schnorr signature aggregation algorithm. And what we essentially saw is that on our current oracles that MakerDAO uses, we saw an immediate 66% gas reduction. So I want to go a little bit more into what our goals were with this solution, what problems we ran into, and kind of like how it ultimately works as a mechanism, and then kind of just run through the numbers. So we wanted one implementation across all chains. This is difficult to do, right? Because on different chains, you're going to have different kinds of characteristics, right? In terms of, compute is very cheap, right? Or call data is very expensive, right? We didn't want to have to support multiple implementations. And that kind of meant that we would have to make some trade-offs, right? So rather than coming up with a solution that's hyper-optimized for one specific chain, we wanted to make a solution that overall was very good on all chains, rather than just excellent on a single chain. Right. The other thing that we talked about, right, was gas prices, right? We wanted to, the ultimate litmus test is, can we survive a 3,000 gwei burst? I can tell you that's not a imaginary scenario. That has actually happened to us, and it's not very fun when you are literally shoveling hundreds of thousands of dollars of ETH into an oracle that's just getting eaten up, in huge $1,000 chunks. And the other thing we wanted to get away from is, you probably noticed earlier in the screenshot, right, the number of validators that we had. So we have 22 validators, and essentially the security of an oracle, if you think of the security as the size of the validator set, is currently directly coupled with the gas costs needed to update an oracle. And that is a really terrible property. You really don't want to make the trade-off of we would love to have more validators, but it would be too expensive for our business model. And so we're just going to settle for less validators, right? Less security. So a big goal of our implementation was that whatever solution we choose, right, we'll have constant time or near constant time verification. So we can decouple this security from cost kind of trade-off that everyone else seems to be making. OK, so immediately kind of two problems kind of were in our face that we had to get around. One, I touched on a little bit earlier, right? On Ethereum layer 1, compute is incredibly expensive. And relative to compute, memory is quite cheap. And on layer 2, you have the exact opposite problem, right? Where you have very, very cheap compute, but memory is extremely expensive. And so you would think with these two environments being polar opposites, how do you come up with a single optimized solution for both of these? So that was a bit of a head scratcher for a while. The other thing is this misconception that just because chains are EVM, right, or say they are EVM compatible, there are huge differences between all of these chains that are calling themselves EVM. I think others like to point out, oh, well, we're going to have precompiles that are going to solve this problem, or like call data in the future will be very cheap because we're going to have proto-dank sharding. I have news for you. It's going to take years for precompiles to kind of pollinate from Ethereum out to some of these other applications. And it's not just proto-dank sharding. It's like all this entire bubble of of EIPs that everyone's like, oh yeah, once we have that, everything will be fine. It's going to be a huge, huge rat's nest. And so what we ran into right away was like, oh, well, you can use this type of mechanism or this type of proof, and there's going to be this precompile that's going to let you verify it super cheaply. Yeah, no, you're not going to be able to launch on every chain in any kind of timely manner that's relevant for kind of taking over your vertical. So essentially, that really limited the type of mechanisms that we could use. So enough complaining about stuff. Like, what did we come up with, and how does it work, and why is it awesome? So we call this an optimistic Schnorr algorithm. If you're not familiar with Schnorr, Schnorr is a signature aggregation scheme, similar to how BLS is a kind of a signature aggregation scheme. Ethereum does have precompiles for verifying BLS, but it's for a version of BLS that is super, super unsecure, and so it's totally unusable. There is a mythical precompile coming that will one day let you verify in a very efficient manner the actually secure version of BLS. Yeah, maybe one day, who knows? But with Schnorr, you can actually verify it in much more effectively than BLS on chain at the moment. And Schnorr has been used in Bitcoin quite extensively for a number of years now, and so it's fairly battle tested. And so what we have our validators do is essentially sign and create this aggregated Schnorr signature, right? So now you have one single signature, and then what we have is one validator essentially signing the correctness of that Schnorr signature. And why do we do that? It's going to be, we're going to get to that in a second. A relay, which is a permissionless kind of function. Anyone can do it. You can even go in our dashboard and click an update button and run the update yourself. This payload is going to contain the Schnorr signature, the single ECDSA signature that the one validator did, whatever the data payload is, which in the previous example was a price, and the timestamp. And so what does the Oracle do? Well, the Oracle smart contract is going to, one, verify that the relayer passed a signature that corresponds to the payload. It's going to verify that the signer of that signature, right, is actually supposed to be a validator, and it's going to verify, right, that the timestamp is relatively recent. And so what happens then is we say that, great, this price is the optimistic price. So notice that we did not verify the Schnorr signature here. All we did was verify one ECDSA signature, and so we've not actually proven that the Schnorr signature. And the reason that we do that, right, is to get these gas savings as low as possible. And so instead, you have this optimistic model where there is essentially a challenge period during which this optimistic price can be challenged. And running calling the challenge function, all it does is actually verify the Schnorr signature itself. And so verification of the Schnorr signature is about, I want to say 150,000 gas. So it's still relatively affordable. And if you run the challenge successfully, what happens? Well, that means that the one validator that attested to the Schnorr signature, that they lied, that they're malicious. So the first thing you do is just ban them and remove them from the validator set. The second thing you do is you drop the optimistic price. And the third thing you do is you let the challenger claim all of the ETH that's in the Oracle contract as like a reward. And now you go in the Flashbots Discord and you tell all of the people running these Flashbot kind of searchers that here is a really good opportunity for you to make a lot of money. So just always, whenever you're building your, whenever you're searching for opportunities, just here's a list of Oracle contracts. See if you can call challenge successfully, and if you can, right, you can claim a boatload of ETH. So realize I'm running a little on time here, but this is my last slide. How does this look like from the numbers? So currently, I have on the right, I have the new optimistic Schnorr algorithm, and on the left, I have kind of your standard ECDSA signature verification, right? As if you were to validate all of the signatures. The gas on the left side is using 13 validators, right? So verifying 13 signatures. Right, if you were to use double the amount of signatures, right, it would cost a boatload more gas than this, right? If you used less validators, it would cost less. But what you're really looking at here is the relative gas amounts, right? So on layer 1, between the two implementations, we're seeing a greater than 50% improvement. And on layer 2, we're seeing an even larger improvement. We're seeing about a 66% improvement. And, you know, once pro-dank sharding is introduced, like, you know, the call data, you know, cost goes even lower. And so like on L2, right, we would expect that 66% number to rise. If you want to put these in a frame of reference to other Oracle providers, Chainlink Oracle update on Ethereum mainnet is between 320 and 340,000 gas. So what we've come up with here is like really pushing it in terms of like how much lower can you get the gas cost per update. Anyways, so we're essentially ready to launch this. So we're really looking forward to September when we finally get to open it up to everyone. And if you want to find out more, if you want to integrate with us, if you just want to talk, you can follow us on Twitter at Chronicle Labs, or get in touch with me personally on Twitter at Nomos Paradox, and or you can join our Discord at chroniclelabs.org. So thank you very much, and happy to take any questions.